In this video, I'll talk about magnetic field due to a long solenoid. Here it's a long solenoid. It should be a long solenoid here. What is solenoid? A solenoid is a long wire and which is winded in the form of helix or a spiral. That is called a solenoid. So here you see it is tightly closed in the form of a helix here. So the current is passing in here and that is coming out here. At this point, current is going in and coming out, going in and coming out. That's how the current is passing, or the current is looping around. All right, and the current is coming out here, and in between here it is looping around the current. And if you look at the magnetic field now, due to this circular currents, this is circular current, then the magnetic field is mostly inside the circle. This just looks like a magnet here, just looks like a magnet here. So the magnetic field, if the current is going this way, the magnetic field will be coming out of the solenoid and then again entering back into here. So it forms a closed loop here. Most of the magnetic field, if it is a long solenoid, most of the magnetic field will be in the solenoid here, and there will be some of the magnetic field outside it. So that is called the fringe magnetic field. Fringe magnetic field. And this is not a very long solenoid. Okay, so how do we find out the direction of the magnetic field? So here I have shown you a diagram here. If you have a current carrying loop, just like a circular loop, then you can find it by using again right hand thumb rule. Right hand thumb rule again. So in this case, what you have to do, you have to curl your fingers in the direction of the current. So here in this case, the current is looping around. So my fingers, these fingers will be in the direction of the current. Okay, so here as it is, then my thumb will point out the direction of magnetic field. So you see, in this case, the magnetic field is in a straight line. So in general words, what you can learn, a straight wire, if you have a straight wire here, a straight wire, then this straight wire produces circular magnetic field. So this is a current, this is current, and this is the magnetic field. All right, and if you have okay, just give me 1 second. If you have a circular current, then you will see a line magnetic field. Okay, so if you have, again one more time, if a straight wire, due to a straight wire, the magnetic fields are circles, or it encircles the straight wire. And if the current is a loop, a circular loop, then the magnetic field will be in a straight line. Okay, so now let's come back here. As the magnetic field is circling around, which in the form of circle, most of the magnetic field will be a straight line here inside it. But outside, as this is not sufficiently long, there will be some fringe magnetic field. Okay, but in this video, we will be calculating the magnetic field due to a long solenoid, very long solenoid, or which has a very large number of turns. The large number of turns could be 600, 700, 1000, 2000 turns, not like five turns. The 5 turns or 20 turns is not a long solenoid. 5,000, 1,000 can be closely called a long solenoid. Okay, so let's find it out. If you have a long solenoid, just like here, so this one represents the upper portion here, and this is the bottom one. If it is a long solenoid, then the magnetic fields are almost uniform, and it is in a straight line here. That is the direction of the magnetic field. Okay, so this is the magnetic field here, this is the magnetic field. All right, and we assume n is the number of turns per unit length. The number of turns per unit length means how many turns you have in a unit length. Okay, so the number of turns in a unit length. Okay, so that is n over L. And you see, as the current is homogeneous, then in each loop, the current that is passing is I. Okay, so the I is the current through the solenoid. Now we're going to apply Amperes law. In order to use Amperes law, we have to draw a loop, a closed loop. So here I have drawn a closed loop in the form of a rectangle here. All right, in this form, A, B, C, D here. And now what does the Amperes law tell you? That B vector dot dl vector is equal to mu naught I enclosed. That is the Amperes law. So let's first find out B vector dot dl vector. Let's first find out this equation here, B dot dl. Okay, so B dot dl. So now I'm going to divide into 4 segments. I'm finding out B dot dl for this line, then this line, and CD and DA. So I'm writing here for AB, BC, CD, and DA. Okay, I'm going to integrate first for the AB, then for BC, then for CD, and then DA. If I add them together, then that will give me B dot DL for the entire loop. Now look at for the AB here, AB path. Now if I look at this AB path here, the magnetic field is along this direction, and DL are also in the same direction. Both magnetic field and the length, elementary length DL, or this length, are in the same direction. Okay, so how I can write down for AB, for this AB here, both magnetic field and loop are in the same direction, and it is uniform. That's the reason we assume this is for long solenoid. If it is not a long solenoid, then it might not be constant here. Okay, that's the reason, which again repeating, it is a long solenoid. B dot L. L is the length of AB here. Now look at this portion here. Now integrating over BC, or we're doing this, calculating this here. The magnetic field over this, if I look at this region, the magnetic field here is along this way, and the elementary length is along this direction. This is the B and this is the DL vector. Both are perpendicular direction. So cosine 90 degree is 0. So this portion is 0. And if I look outside the solenoid, the magnetic field is 0. So this, for if I integrate over BC, it is 0. Okay, for 2 regions, the magnetic field here is along this direction, and the elementary length is along this direction here. Both are mutually perpendicular. So inside it is 0 here. Now if I look at outside, the magnetic field is 0. There is no magnetic field, so it is 0. So this term is 0 now. And now look at the CD now. For the CD here, you can clearly see there is no magnetic field here, so this term is again 0. Now let's go back to DA, or for this line here. The same thing here, it is again 0. Why it is again 0? Because the magnetic field is along this direction and the DL is along this direction here. Both are mutually perpendicular. So if it is perpendicular, then cosine 90 degree is 0. Remember, this is a dot product. The way it is defined, b vector dot dl vector is b dl cosine theta. If b vector and dl vector are perpendicular, then this will be 0. So the only term that I have here is bl here. So we integrated this term and get bl. What is L here? L is the length of the AB here. Okay, the length of the loop here. Okay, so now let's plug in into the Amperes law. This is the Amperes law here. B vector dot dl vector is equal to mu naught I enclosed, and this I enclosed is the what is the total current enclosed by this loop here. How do we find out? So see, it does have the loops here. Many loops are passing through here, and each loop has a current I. Okay, each loop has a current I, right? Because the same current is looping around. So the total amount of current, now if it has more turns here, more turns means the more current will be enclosed in this loop here. So the total current can be given by this equation here. N is the number of turns per unit length, that in a unit length, how many turns it does have. And I is the current in each loop. So the total current enclosed is given by NLI. This is the number of turns per unit length, which is N over L. If the total length of the solenoid is L, then this is it, L times I. So this is the enclosed current. So now L and L will cancel out and we'll have this magnetic field, mu naught Ni. Remember, this magnetic field is for a long solenoid. This is for a long solenoid. Okay. And what does it tell you? This is a uniform magnetic field. It does not change inside. So it doesn't matter whether I measure here, 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 here. At any point, the magnetic field is constant, uniform. So the solenoid, in fact, is used to produce a uniform magnetic field. Okay, if you have to produce a uniform magnetic field, you'll use a solenoid, a long solenoid. So now see, how does the number of turns changes the magnetic field distribution? If you have only one turn, then the magnetic field will vary like this. And if I keep increasing the number of turns here, then more and more magnetic field it passes through inside it. And if I keep increasing it, then the more magnetic field passes in. And if I make sufficiently long, then the field gets uniform. It gets more uniform and uniform, and there are less fringe fields here, a smaller amount of fringe fields. And if I make it sufficiently long, even long, then it will almost produce a uniform magnetic field inside. Okay, so if you have to produce a uniform magnetic field, then you have to choose a long solenoid. Okay, and remember, in this equation here, N is the number of turns per unit length. N is the number of turns per unit length. So this is it from the magnetic field due to a solenoid. If you have any questions, write down your questions in the comment section below. And do not forget to like, share, and subscribe the channel.